Well, hello to everyone and good day. First of all, I want to thank Laser Focus World for inviting me to speak. I always appreciate being asked to speak and these forums to speak. And I've really been excited about the PhotonicsNXT conference that they have organized. And I hope you get as much information as I hope you will get out of this tech talk entitled Characterizing Laser Performance from Front to Back. Just to give you a little bit of information about myself, my name is John McCauley. I'm the Business Development Manager for the Americas for MKS Instruments, specifically the Ophir laser measurement line. Let's talk about an agenda for today's talk. I first want to talk about the importance of characterizing a laser throughout its life. If you think about a laser's life, the laser is a lot like a human being, right? It starts off as an infant. It grows up into what it's what it's going to do for the rest of its life, and then towards the end of its life, like a human being, we see some problems, health problems and whatnot. And so it's important to characterize a laser a lot like you would a human being. Would like to then go into important and typical laser parameters to measure. So what parameters should be measured during a laser's life, and when should those parameters be measured? We want to talk, of course, about how to take these measurements and how to analyze the measurements and analyze the data that you have collected. And then finally, at the end of the talk, I want to talk about some laser applications where the concepts that we're talking about today have made a difference. Let's talk about automotive welding in application development and in production. We want to talk about additive manufacturing systems, and then finally the development of LiDAR products, because that's a very hot topic these days. No matter how a laser is used, the success of a laser depends on a consistent performing laser. If your laser starts off as an infant during the source development, and if it's inconsistent during that part of the laser's life, then common sense will dictate that throughout the laser's life, it's going to be an inconsistent process. So ensuring consistent laser performance is really crucial throughout a laser's life. We talk about the source development. So when the laser is in its infancy, ensuring that laser is going to remain consistently performing throughout its life is part of what source manufacturers ensure, and that's how they actually make the sale to their customers is communicating to them that this laser is going to remain consistent in its performance. Here's how it's performing. Here's how it's going to perform throughout its life. You take that laser source, and then you move it to an application development phase. How is that laser going to be used? Well, the laser must be remaining consistent in its performance during the application development, because if it's not, it's going to carry over into the next phase of its life, the system integration. You take that laser source, you integrate it into a system, and you want to make sure that laser is performing at that time as it was designed to. So as want to make sure that it is performing with respect to its design characteristics. And then finally, once that laser is commissioned and put into production, you want to make sure or ensure as best you can, as that laser ages, that laser is remaining consistent in its performance from the time it's commissioned to the time it is decommissioned. This is achieved through performance and measurement analysis. You really can't ensure that the laser is remaining consistent in its performance without measuring and analyzing and referring to past measurements about how that laser is performing. So that's what we're going to talk about today. Let's talk about some important parameters to measure over the laser's life. I think most everybody is familiar with laser power meters and measuring the laser power or energy, and recognizes those measurements as a vital way to measure how that laser system is performing. This laser power is and energy is the amount of light that's being applied to the process, regardless of what the process is. If you're talking about a pulsed laser, then the pulsed laser characteristics, your pulse width, your pulse shape, pulse frequency, these are all vital pieces of information to understand about how these parameters affect your process. Then you're talking about a beam profile. You're going to talk about beam geometry. So this is how the beam is shaped, how the energy is distributed across the beam, whether the beam is round or off round. All these measurements or all these characteristics are vital to understanding the performance of the laser. Beam size, focus spot size. So you've got an amount of light and it's being applied to your process somehow. You need to understand what the beam size is as it applies to your process, because that's going to ultimately affect how that laser is interfacing with your process. And then focus spot location, when we're talking specifically about high powered lasers and the thermal effects that might cause the lack of or the degradation of the performance of that laser, we need to understand if there is some kind of focus shift, or if there is some kind of shift in the location of the focus spot, because that's ultimately going to affect how that laser is interfacing with the process. More so on the front end, but also I found that some automotive customers like to measure these parameters when a system is integrated. We're talking about laser quality measurements and Rayleigh length measurements like M squared, beam parameter product, your K value. These are all indicators of the laser quality and what kind of laser quality you're getting from the source specifically. And then ultimately, when we're talking about industrial lasers specifically, the power density. So this is the amount of laser light with respect to the beam size that's being applied to the process. So if you have, for instance, a cutting application, you need to know how much laser light you have through a power meter check, as well as how tightly your focus spot is down on the material, because the laser is going to process that material at a specific power density or power density range. Let's talk about measuring and analyzing these laser performance characteristics and how these measurements are taken. We're talking about laser power energy and your pulse characteristics. I think most everybody is familiar with the concept of the power meter. You have these power and energy sensors which collect the laser light, and then they are combined with some kind of meter or a PC interface to actually give the readout of the values on the handheld display or your PC. Ophir also makes a couple of all-in-one products, and these are just like they indicate, it's just they collect the laser light, they do the analysis all in one product, and so these are somewhat convenient to use. But if you do want to get into a more full analysis of what your laser light is doing, having the software running on your PC and taking that information and being able to analyze in further detail what your laser is doing, specifically over time or short durations of time, to have that PC software to take that analysis is also very useful as well. When we're talking about beam geometry, beam size, focus spot size, then we're talking about a beam profiling type situation. In the middle here is a product that Ophir makes. It is a beam splitter assembly. It's coupled with a camera. It basically reduces the signal that reaches the camera to a suitable level, and then once that signal is interfaced with a computer, you see on the analysis software there, you're seeing the shape of the beam, you're seeing the size of the beam, you're seeing the roundness of the beam. All these parameters that you see in the upper left here, there's a wide variety of parameters that you can measure from a beam profile. That's a camera-based beam profile. Pictured here at the right, this is a scanning slit profiler. It's just a different way of acquiring a signal. It's very, very good for putting into the beam path of relatively low lasers and collecting focus spot size. And it's also very good for small beams as well. So measuring very, very small beams, it does an excellent job on getting the beam size data on that particular beam. Laser quality. Again, laser quality is typically measured at a source development. But like I said, more and more manufacturers are becoming more interested in the laser quality measurement. So M squared, beam parameter product, the K value. These are some of the some of the characteristics. Pictured here is that is an M squared analysis machine built on the scanning slip profiler technology. It's called the Nano Mode Scan, made by Ophir. And then pictured to the right here is the it's called the beam square. This is a camera-based system. It effectively does the same thing. It moves both these systems. It moves the data acquisition device through the beam waist and analyzes the beam waist on the front and the back end of the focus spot and gives that information about the Rayleigh length and specifically about how the laser is focusing at the workpiece. And then some people are interested in measuring, several bits of information about your laser. So the beam size, the focus spot size, focus spot location is very crucial to understand for high-powered industrial lasers. In addition to laser quality, again, the M squared, the BPP, all very useful bits of information. So here's a device. It's called the Beam Watch. It's made by Ophir. This is specifically for kilowatt lasers at around 1 micron wavelength. It's a non-contact beam profiler, but the beauty of it is, since it's camera-based, it's looking at the beam waist simultaneously at one time. So you're getting the laser quality information. You're seeing the focus. You're seeing the focus drift happen real time, and you're able to measure that and how much and how quickly your focus spot is shifting if you have some kind of thermal effect on your laser system for the multi-kilowatt fiber laser. But ultimately, it's when we're talking about industrial lasers, we're talking about power density. We're talking about how much laser light is being focused down to what kind of spot size. And Ophir makes a number of all-in-one systems that measure not only the beam profile, not only focus shift in most cases, but also the laser power or laser energy at the same time. So all that bit of information is collected into one place, and you're able to analyze the overall performance of that industrial laser at one time. Finally, let's talk about some industrial laser processes where lifetime performance characterization made a difference. And again, we're talking about measuring the laser from the laser source to the application development, to the system integration, all the way out to the production and the commissioning of your laser. Because measuring your laser at all of those laser life cycles, points in the laser's life cycle, are very important to fully understanding how that laser is performing over time. So let's look at automotive laser welding, a couple of different examples. Let's look at an additive manufacturing system, and then finally let's talk about LiDAR product development. This particular laser application is aluminum on-the-fly welding. Aluminum is very tricky to weld with respect to all the different materials out there. It's a little more tricky. There's a lot more consideration given to power density. So power density certainly plays a more vital role when you're talking about aluminum welding. This particular lab had a 6 kilowatt fiber laser that was doing on-the-fly welding. On-the-fly welding is I don't know, for lack of a better explanation, the laser components are moving as it's welding. So it's not stopping and welding. It's actually moving, so to save on the cycle time. So this was on-the-fly welding in an application development type setting. What this particular lab was experiencing was a loss of weld penetration. So that it was a relatively long weld that was penetrating at the beginning of the weld. Then as the weld went on, there was loss of penetration. So they suspected some kind of focus shift, but they didn't really know exactly what was happening. You see the measurement equipment pictured here. There's a 10 kilowatt water-cooled sensor at the floor there. had a relatively long focal length lens that we're dealing with. So we had to keep the power density low at the sensor, coupled with a meter. In this case, it was a starlight meter, and then the beam watch beam analyzer to analyze focus shift. So collecting all that bit of information, what we determined was that there was a contaminated window causing focus shift. So it was either contaminated window or a window that had its anti-reflective coating that was starting to break down. But at any rate, it was this protective window that had started to cause a thermal effect on the laser system that caused a loss of power density. If you think about what the laser is doing, it's focusing down to a spot, and if you have a drift of that focus spot, so when you turn the laser on and as it goes up, what's happening at the work site? The work site, the beam size is increasing, right? So as the beam size increases, then you have a decrease of overall power density for the same amount of laser power. So obviously that's why there was a loss of penetration at the end of the weld. The second application is a copper to copper and copper to aluminum busbar welding in a production environment. So what there was a 2 kilowatt fiber laser welding in production. And what was happening was that there was a loss of penetration at the end of the cycle. So there were a number of welds that were happening. The first few welds were penetrating fine. And as the laser continued to process these welds on this battery pack, towards the end of the weld, that they started to lose the weld. Again, they suspected some kind of focus shift, but they didn't really know for sure exactly what was happening. The measurement equipment that we used, there was an integrated power meter system on the laser system to collect the amount of power to make sure the power was fine. And then again, we used the Ophir beam watch, which was the non-contact beam analyzer to analyze any focus shift that might be on the system. What they found was that what they ultimately found after a couple of visits, taking measurements, was that there were some poor maintenance practices in place. Now, this was a fiber laser, so at around the 1 micron wavelength, optics are very susceptible to contamination. And what they found was that there was a poor maintenance practice that was in place, and it was ultimately, I think it was causing some contamination of the overall system. So this was resulting in that focus shift. There was a focus shift, and again, it was a loss of power density that was happening at the work site, which made sense for the same amount of power. If the beam size is increasing at the work site, your power density is going to go down. So that's why there was a loss of weld penetration. This next project that we got involved with was an additive manufacturing system in a research environment. It was a 1 kilowatt ND-YAG laser, and this particular system had free space optics, which is kind of something of the past, but it was a research situation, so they were limited on money, so they had to work with what they had. But it was free space optics in a research lab. And what they were experiencing was a loss of joining between layers. So the first few layers, or the first part of the layer, would join fine, and then towards the end of that laser process, the scan of that particular layer, they would lose penetration. They were experiencing some holes and some just general lack of joining. And so they called us in to see what was going on. This particular application, we used an Ophir 5000W water-cooled sensor with a Vega meter, which is not pictured in the picture, and then the beam watch beam analyzer to tell us what was going on with the focus shift. What we measured was about an 8 millimeter shift, focus shift from the work site up. And which was obviously causing a lack of power density, which was translating into a loss of joining. So what we started to do, we started to troubleshoot the optics. Very easy to do on this free space optics system. We started at the cover glass. We started at the focusing lens. Both of these were relatively clean. And then we worked up, and there was an optic upstream of the focusing lens that you see here, that it was, obviously you can see it was very dirty. So we took about 10-15 minutes or so and cleaned this optic, put it back in, and lo and behold, the focus shift went away. So it was because of this neglected, contaminated optic that I don't even think they knew the optic was there, to be honest with you. But we found it and we cleaned it, and then lo and behold, it took away the focus shift. Okay, and then finally, let's talk just briefly about LiDAR production product development. So LiDAR products typically are using very low, or relatively low power diverging beam. So from a point source, it's starting to spread out. That's what a diverging beam means. At near IR or mid IR wavelengths, there's several different wavelengths that are being used and experimented with. But with respect to product development, there are a ton of challenges that these guys have. Number one, the goal really with LiDAR is to maximize the laser signal, all while remaining eye safe. So they want to put as much laser light out as possible, because that's going to generate the more higher resolution images and the maximize the signal coming back. But there's also the consideration of remaining eye safe. So they can't just shoot out laser light all willy-nilly and expect everything to be okay. There has to be some consideration to eye safety. So knowing the power that's being output from the LiDAR system is crucial to understanding and to developing these systems. Also, with respect to lifetime consistent performance, if you're not measuring the laser power and knowing what your light is doing as you develop the products, then how can you possibly know what your product is going to be doing once it's integrated, for instance, onto a car or wherever it's being used? How are you going to know that it's going to remain consistent over the lifetime of that that car or whatever else you're using it for? So several different measurement equipment solutions that are out there. Pictured here is an OFI, or integrated sphere. What an integrating sphere is, it measures laser light, the diverging light source, by allowing the light to illuminate a sphere and then take a relative measurement from a sensor that's attached to it. This is a product is just came out earlier this year. It's called the Wide Beam Imager. It's specifically designed for measuring point sources, such as a VCSEL, source. And you see here some images that, and you can see how the mode changes as you apply different currents to that particular VCSEL. So understanding this information, not only your power, but what your beam is doing with respect to its geometry, is crucial. It's vital to understanding this information as these products are developed. So just to summarize very quickly, ideally a laser should perform the same over its entire life. I think I've proven that today. Regardless of how the laser is being used or where it is in its life, there will be changes in the system components which affect its long-term performance. And really, the only way to really fully understand how your laser light's performing over time is through the measurement of it throughout the laser's life. Managing these changes is vital to the product's success. Laser performance measurement solutions are there to help you achieve this success. Again, thank you so much for watching. Thank you for joining me today. There's my information. If you have some questions about your specific application, I'm always here to help. And thank you and have a good day.